hurt the logistics in the calendar. Okay, you guys should have filled some of this in on Friday. So you teach me. I mean, I taught you, but you teach me as far as what these things are. So what's an outcome? Some of these wordings earlier, because we talked about the formula, didn't we? We'll fill in what it means, but we talked about a fraction. We talked about probability a little bit earlier in section 9.6. But yeah, sorry, result of a what?
Trial.
Oh, of a trial. So I don't need an N, of a trial. You could do trial, you could also do experiment, that could also work. I guess it would be, yeah, I guess we could. All right. There you go. Sample space, what's going on there? All the possible. Yeah, good. All possible outcomes. Plus unfavorable. But down here when we're doing probability, sample space is the bottom, the denominator, the whole group of all the different outcomes. So this one down here, n, we're used to n, aren't we? N is like a number. So n is the number of the sample space, how big the sample space is. So you can think n is for number and the number of options in the sample space. What's going on in the numerator? Outcomes. So you could think number of favorable outcomes. But why does it say E? It says E because, yeah, another way of saying trial or experiment is also the word event. However, event, well, hold on. Trial is just the whole thing. Experiment is the whole thing. Event is a little more specific. So event actually, that's why I didn't write it up here, goes with favorable. So the event occurring or the condition being met, the favorable outcome. So this is probably a little bit more descriptive, a little bit better explanation. Favorable outcome, the trial or the experiment meeting whatever condition, but you could also say of the event. So like I think on, was it Thursday? We were talking about flipping the coin. Maybe it was Wednesday. Wednesday or Thursday, we were talking about flipping a coin, and I said something about of getting two heads. And we were flipping a coin 3 different times. How many ways can we get 2 heads? That would have been the event. But you didn't necessarily have to get 2 heads. So there were more possible outcomes in the sample space, but the event was 2 heads. The favorable outcome was what if you got the 2 heads? Joe?
What is the event horizon?
Event horizon? Oh, you're not talking about the page. You're talking about something else? Yeah. Oh, not something that we need to worry about. Okay. Did you guys get to special probabilities? Yeah, cool. So special probabilities. What if the probability of the event, you guys have to learn how to read this. The probability of the event occurring is 0, or the probability of the event occurring is 1. If it's 0, what ended up happening? Yeah. The event cannot occur because it's what kind of event? Impossible. Look outside. Is the sun shining?
Yeah.
What are the chances of, well, hold on, I can't make it 0. But I can say, what are the chances of the sun shining today? And you could look outside and say, oh, 1 or 100%. That's the opposite of 0. We'll talk about 0 in a second. If you look outside, the sun is shining. What's the probability the sun will come out at least once today? You're like, well, it's right now, so yes. The event is certain. It's guaranteed. Yeah, I did it weird. I forgot there's no verb. What did I put? Is guaranteed or is certain? Will occur. Ah, there you go. We can say it's a certain. It's the blank that's right next to it. You guys are geniuses. Oh. Nice. Oh, well, thank you. Come on. Thank you. Trying to be lazy, it'll take more time. Have you guys ever done that? Tried to do something the lazy way and it ends up being harder than if you just did it the normal way? Same. There you go. Okay, so I say, what's the chances? What are the chances? What are the odds? What is the probability of the sun shining? You say 1. It sounds so small, and yet it's 100%, 1.00. It's guaranteed. The event is guaranteed. But what if you look outside and it was raining? And I said, what are the chances of it not raining today? If you look outside and it's raining, 0, because it's raining. It's already happened. Too late, too bad, right? So that's the difference between 0 and 1, guaranteed or impossible. But what if I was to tell you to look outside right now? The sun is shining. What are the chances of it raining today? 0. Well, today hasn't happened yet. What do you mean 0? 100%. Well, it's not raining right now. So then you have to go to meteorology and go to weather reports and hope that they're right for today, right? And then there's the whole science behind how they're making those predictions, et cetera, et cetera. But there was someone's birthday recently. No, it was a lady. And she did a lot of work with differential equations. I forget her name. She was Russian, I think. It was actually kind of a cool story in the sense of, like, her father was seen as some sort of spy or something in the Soviet or the communistic government. And so then they killed him, and then they outlawed her from going to college. And then she was a female, so they didn't really care even when she could go to college. And then it was this whole thing. But anyway, she did a lot of work with meteorology and climate prediction and stuff like that. But anyway, it's harder than it seems. 0 is kind of easy. 1's kind of easy. Everything in between is where it gets fuzzy, right? Down here in the example below. You toss 2 coins. There we go. You toss 2 coins. What's the probability that both land heads up?
1/4.
How come?
There's 4 outcomes total.
4 outcomes total? How do we know that? Couldn't we do fundamental counting principle? There's 2 ways to land and 2 ways to land. There are 4 total possible. That's our denominator. Heads, heads, tails, tails, heads, tails, tails, heads. That's easy. We can count them up. But which or how many of those are heads, heads?
1.
Just 1. So yeah, we could say 1/4. We could also say 25%. We could also say 0.25. Your answers in homework might all look a little bit different. Decimals are okay, percentages are okay, fractions are okay. Letter B, though, well, it just got a little harder, unless you know cards. You draw 1 card at random from a standard deck of playing cards. What's the probability? It's an ace. Let's pause and talk about a standard deck of playing cards. There are lots of different decks of cards, but the most common ones are playing cards. So with playing cards, we need to talk about some details. First of all, why do we need to be careful when I ask you how many cards are in a standard deck? Yeah, whether or not you count the jokers, right? So let's assume the jokers, do I even have jokers in this deck? Oh, I do. Here you go, random jokers. Most games you don't play with those, right? So how many cards are in a standard deck, not including the jokers?
13 times 4.
Otherwise known as 52. So we have a total of 52 cards. I don't think in homework the jokers are ever included. That's great. We're just talking about a deck of cards. So these deck of cards, how many different colors do we have?
4.
How many colors? 2. So this is split into 2 different colors. So we have 26 red, right? And we have 26 black. Unless you have a weird deck of cards that, I don't know, has different colors than that. Okay, how many suits are red? 2. Which ones are red? Hearts or and? Where are diamonds? Whew, it took me a while. Hearts and diamonds, right? So we have 13 that are going to be hearts. And we have 13 that are going to be diamonds. How about black suits? So we have 13 clubs, and we have 13 spades. I mean, it's kind of obvious so far. We have total, and then these are our colors, and then these are our suits. Okay. Now, once we get into, and I don't want to keep branching out, it's going to take forever, but each of these suits, okay, Each suit contains what? 13 cards, but what about those 13 cards? They're all in common. What kinds of cards do they include? Every single suit has what? Huh? Some are numbers, so what numbers are there?
10 through 1.
Not one.
1.
Okay, so we have numbered cards, right? Which are 2 through 10. What else do we have?
Face cards.
Face cards. Specifically by face cards, we mean Jack, Queen, King. There's 3 each, right? So 2 through 10, that's going to be 8 cards. 9, 10, 11 cards. Wait, nope, sorry. 9 cards, 10, 11, 12 cards. What's the 13th card? Ace, which can be low, can be high, can be all sorts of things, right? So with all of that information, when it asks me what's the probability that you draw one card at random and it is an ace, sample space, how many total cards do we have? 52. And how many aces could you get?
4.
Got it. Done. Now, can't you reduce that?
Yeah.
So we could just say, how could you have gotten here?
Because 52 is divided by 1.
Because each suit has 1 ace. You could also think of it that way. Each suit is going to have 1, or our entire deck has 4. But either way, we have it. Yes, we could do decimals and percentages, but blah, that's good. But what if it gets a little bit harder? Now, if you want, we can kind of see, I think I have an example right here, where it's not just one thing being chosen, but more than one. Okay, hold on. We need some more principles. And this will go together with the cards as well. We'll come back to the cards in a second. But so far, it was pretty easy. What are the chances of you getting a 2, of you getting an ace, of you getting a red card? Just take 52 as your sample space and think of how many ways that characteristic could be met. But we're getting to harder questions, so we need to talk about a few techniques. One of them is intersection. Intersection of events. Now, we've heard this in math multiple times this year. Intersection of graphs, where one function is true and another one is true. A shared point, an intersection point. A shared point, an intersection point. I see some people writing, so I'm thinking we're to new stuff, right? Or no? Almost. Intersection, keyword and. Probability of events A and B occurring. You guys recognize what this is, right? It's a Venn diagram. Yeah, it is. Venn diagram, we could say like all the different ways A could be true, all the different ways B could be true. But if I show you this Venn diagram that's overlapping, what am I saying?
Sometimes it can be off.
Yeah, sometimes it could be shared. There could be overlap. They could both be true. What's an example of something in a deck of cards where more than one thing could be true?
It's black and it is 4.
Yeah, that could be one way. What's the probability of you choosing a card and it's a black card and a 4? Well, couldn't you think of all your different black cards? And couldn't you think of all your different 4s? Thank you. All your different black cards and all your different 4s? I'm not sure exactly how he wants me to do this. I'd rather not, but I figured he came in anyway. Sorry. You're welcome. Oh. Oh. More love, guys. More love. Okay. Tardies, you got to get to class on time. Sorry. Probably. First period's the hardest one, right? Okay, coming back. Probability of events A and B occurring. Is it possible for there to be an overlap? Is it possible for both A and B to be true? So if I was to shade this overlap, just right now, because we're going to use it a few different times, the shaded is what we would call the overlap, where both A and B occur. Now, there is some notation for this. That's going to be the probability, capital P, when or of, that's our parenthesis, our function notation. A is A occurring. Little upside down U actually stands for the word and. Could be an upside down U or like a upside down V or an A without a line through it. Hey, an A without a line through it. Why is that helpful? Oh, anyway, way of remembering it. Haven't we already talked about and in section 9.6 though? What did we do whenever there was an and in section 9.6? Multiply. Same thing here. Probability of A occurring and B occurring. Now, there are different ways of this happening. One way is to say, okay, two separate events happen. You get a heads and you get a tails. And that's something where there's not really an overlap, but it still has the word and. So we have to kind of read a question very carefully and figure out what kind of and is it. So I'm going to put a quick note down here at the bottom. What kind of and is it? We have to ask ourselves, whenever we see the word and, is it something like a combined characteristic? In one event. Is it a combined characteristic in one outcome? So like what Joe said, he said black 4. Well, that could be you picking a card out of the deck. It needs to be a black and it needs to be a 4. It needs to be both of them at the same time, which is possible. It's possible for have all your black cards, all your 4s. It's possible to have a black 4. So that's kind of what this one is talking about. This one's talking about a combined characteristic. One object, one outcome, having two different things being true about it. But there's another way, and that's what section 9.6 does, or section 9.6, how the word and was used. It could also be used, and I have to put an or, sadly. Combined characteristic, more than one thing true about one outcome, or a connection between multiple outcomes. So is it just saying more than one thing needs to be true about one outcome, or is it a connection between multiple outcomes? This formula, even though this is talking about a combined characteristic, more than one thing being true and is appropriate, and that's one use of the word, but this one down here is actually talking about the connection between multiple. But either way, the idea of multiplication is going to be helpful for us. We're going to keep that idea of multiplication and. But the word and can be used in two different ways, and so we kind of have to be careful whenever we see the word and. Is it just saying, hey, more than one thing has to be true? Or is it saying that it's a connection between multiple outcomes? Let me show you an example, okay? This one's kind of hard to see. What if I was to ask you, what's the probability of choosing a black 4 when you're choosing one card versus what's the probability of choosing two cards? And when you choose two cards, you get a black card and you get a 4. So one is the probability of choosing one card, getting a black 4, and the other one is probability of getting a black card and a 4. Okay, this top one. What are the chances of you getting a black 4 if you're choosing one card out of the whole deck? I agree the 52. I don't agree with the 1 or the 4, though. Why 2? There are 2 different suits, 2 different black suits with a 4. Does that make sense? So you could say 2 out of 26. Wait, can't we go more? 1 out of 26. When you reduce. But this one, aren't you choosing 2 separate cards? Did we have to multiply to get this? No, but it's a card that's both black and a 4. But all we had to do was narrow down, oh, which of these are both characteristics at the same time? We found there are 2 cards in that little overlapping region, 2 cards that are both black and 4. But down here, it's asking for us to separate and say, okay, what's the probability of choosing a black card and then choosing a 4? Is 1/2 or 26 out of 52 are black, right? But why does it get complicated when we go here? 4 out of 52 would be the next one, except what don't we know? You chose a black card, and then you chose a 4. But what's the struggle? This one, it doesn't matter what color the 4 is going to be. That's totally true. And also, do you know what you chose here? You chose a 4. How many are left in this one?
3.
So is it really possible to know without knowing is it actually possible to totally know the probability if you don't know what the first card was that you drew? Have you guys ever heard of counting cards? What game is that with? Not that you shouldn't be able to count cards. You can. Well, there are different ones. Mostly it's the game 21. That's the most common one that people get in trouble with. Ask Mr. Che about it. He is much more of an expert. Anyway, but coming back. He likes to talk about it. But coming back. When you're playing a card game, I mean, to some extent, when you're given your first hand, you're kind of given all the cards all at once in some of the games, in most of the games. But then when you're drawing a card one at a time, don't your chances change based on what you just drew?
Yeah.
Right? Like, your chances change continually. So this is actually kind of a bad question in the sense of like, well, what was the first card? That's going to change your chances for the next card. But do you guys at least get the difference as far as like a black 4 card that has 2 characteristics but only 1 card versus 2 separate events, 2 separate pickings? Does that kind of make sense? They both use and, just in different ways. So let's check out this guy. A random number generator on a computer selects 3 integers. 3 integers from 1 through 20. What's the probability that all 3 numbers are less than or equal to 5? What do you guys think? If a computer's spitting out numbers, could it be repeated?
1/5 times 1/5 times 1/5.
Could numbers be repeated?
Yeah, you can.
It's not like pieces of paper that are numbered, and so once you pick out one, like, hey, it's not there. Instead, it's just choosing from the same numbers every single time. That's why, if I was to have you guys all stand up right now and randomly spread yourselves around the room, like I was to turn around, I'm like, okay, just randomly spread. No, don't do it. Don't have time. Chapel day. But if I had you stand up and randomly go around the room, and I was to turn around, what do you think I would see? It wouldn't be random, though. You were supposed to randomly distribute yourself. There should be someone all over the place. But here's the ironic thing. If I look around the room, I bet you guys would be fairly evenly spaced. Why? Maybe a mind trick, maybe a personal bubble issue, maybe a, well, they're there, so I can't be there, so I'm going to be over here. But as soon as you do that, what did you just make your selection? Not random. Because in random lists, there are going to be random clusters of like repeated numbers or numbers close to each other, numbers far. It's not going to be evenly distributed. So if I were to look around and see even distribution, I'm like, well, that wasn't random. There was totally a plan behind it all. We could actually go into the whole thing with creation, but come back for right now. So if it's random, these could all be the exact same number, or they could be like one right after the other, or they could be some who knows what super spread out. But the probability won't change. The probability says, okay, what are the chances of getting a number less than or equal to 5 for the first number? 5 out of 20, right? 5 out of 20 is same thing as 1/4. The computer can choose the exact same, and the computer can choose the exact same. So it's going to end up being 1/4 cubed. Why? Because it needs to pick a number less than or equal to 5, and a number less than or equal to 5, and a number less than or equal to 5. So we could just multiply their probabilities and say 1/4, 1/4, 1/4. So the same way, guys, we were using the fundamental counting principle for section 9.6 to figure out how many. We can do that for numerators and denominators. We can do that for whole probabilities. We can multiply whole probabilities together. And we'd end up with 1/64. Boop. So, how about this one? What's the likelihood of you drawing a red 4 from a standard deck of cards? No multiplication, because you're just looking for the ones that have both. Do you guys see the difference? You just did the difference. This one, 3 separate. This one, 1 with 2 characteristics. Both are using the word and, just differently. Kind of makes sense? So what about or? Ooh. Okay, what about or? Oh, come on. This one's nice because or is just, well, his letter or his symbol is at least the first letter of his word. I'm not sure if that totally helps, but U is for union. Union, isn't that more like an and? Oh well, not our job to question why. Union. Probability of events A or B occurring. And the same Venn diagram could possibly be a thing, could be a situation. But there are 2 different ors. Now, I'm going to set up the formula. A or B. Probability of drawing a red or a black. That's 100%. Probability of drawing a red or a 4. Not always true at the same time, but sometimes. There are 2 different ways to think of ors. They're not ands. They're not multiplication. Ors, addition. But why are ors addition? What's the probability of you wearing a navy polo or a black polo today? Wouldn't you have to go to your closet and think of how many navies and how many blacks you own? How many navies and how many blacks? As soon as I said navy or black, didn't I just broaden your options? Didn't I just expand the number you can choose from? Didn't I just add to the possibilities? Ah, or means add. Or means add. You now have more to choose from. You now have more possibilities or more options, etc. So maybe that addition makes sense, but why on earth am I going to do a subtraction here, but not there? Subtraction. Wait a minute, hold on. Not subtracting that, though. That doesn't make sense. Why would you add them and take them away? But why am I going to put an and in here? The one I just gave you, navy or black, those are 2 mutually exclusive events, because either your polo is navy or it's black. Do you have any navy black polos? In this school, this uniform, are there any navy black polos? No. You cannot have a navy black polo at the same time. But what if I was to ask you for the probability of choosing a red or a 4? Yeah, there are some red 4s. So if you count up all your red cards and then put them all back, then count up all your 4s and add the 2 together, oh, didn't you just say the red 4s count twice? When there are really only 2 cards, you would have actually made them cards. So some events can be shared. Some events have overlap, and we have to subtract that overlap, and some don't. And so we don't even have to worry about it. We kind of just have to pay attention to the situation. So in this one, probability of black or numbered, 26 out of 52 black. Numbered. Well, aren't there 9 per suit? And 9 times 4 is 36. 36 numbered cards. Yay, I'm done. 50. 62 out of 52. You never want to see that in probability. That's bad. Why was I wrong? I forgot that half of the numbered cards are what color? Black, but half are also red. I had to take away the half that just got double counted, and now I have an accurate OR. Does that make sense? All right, tackle homework tonight. Let's see how we do. I think you have lots of homework helps. Zip, zip. There's one idea we didn't get to. I'll see if you guys, just lots of examples. I'll see if you guys find it in homework. I'm here during 7th and a little bit after school. Yeah.